Right. Today we are going to start the algebra lesson. Right. So basically we are going to introduce real numbers. What are real numbers? Then discuss other types of numbers and introduce the concept surds. Then do some questions involving simplification of surds. Right. So first let's look at what is a real number. In simplest terms, numbers that you can plot on a number line are called real numbers. So any number you can plot on a number line is a real number. So it can be negative numbers, it can be zero, it can be positive numbers, it can be any fraction, any negative fraction, or it can be irrational numbers like e or like pi. So any number you can plot on a number line is a real number. So all the numbers that you learn in O levels are real numbers, right? Okay, so that's the first concept we learn, real numbers. So that's then some notations and definitions we have to learn. So all real numbers, the notation is this: r. R represents all real numbers. Then r with a plus sign represents all positive real numbers. Then if you want to include the 0 with all positive real numbers, you put a 0 like this here. So r plus 0 means all positive real numbers with 0. Then similarly you can define what? R negative means what? Negative real numbers. R negative with a 0 represents negative numbers with 0. Right. Those are the notations for real numbers. Then integers. Integers are what? Those are all whole numbers. Any whole number, positive or negative, with 0 is what? Called the integers. Integers are represented by Z. Then using this notation we learn here, Z plus would be what? All positive integers. 1, 2, 3, and so on. And similarly you can write what? Z minus. Z minus means what? All negative integers. And if you want to include 0, what do you do? Plus 0. That means what? All positive integers with 0. 0, 1, 2, and so on. Right. So these notations can be extended to integers also. Integers, any other numbers also. Right. So we have now defined what are integers. Then the next number type is natural numbers. Natural numbers are also called counting numbers. You count 1, 2, 3, so on. So this is actually all positive integers. So natural numbers are all positive integers. So that is this set, right? Then the next set is rational numbers. Rational numbers are defined like this: x is a rational number if it follows these conditions. X can be written as a fraction like this: p over q, where q cannot be 0 because why? We can't divide by 0, and p and q are integers. So any number that can be written in this form, p over q, where p and q are integers with no common factors. So they can't have any common factors also, with no common factors. Then those types of numbers are called rational numbers, right? So 1 over 3, that's a rational number. Why? it can be written as what? P over Q, where P is 1, Q is 3, and P and Q are both what? Integers. And you can write any integer as a rational number also. Any integers are rational also. Why? 5 can be written as what? 5 over 1. So that is the rational number form, P over Q. So any integer is also a rational number. Remember that. Right. Now, this is also important. This is an easy way to remember what type of numbers are rational numbers. So rational numbers are made up of what? Terminating or non-terminating recurring decimals. So 1/3 is what? Non-terminating, 0.33333. So that's a rational number. This is what? Terminating. 0.125 is what? You can write it as 1 over 8. No? So those types of decimals are all rational numbers. Terminating and non-terminating recurring decimals. Those are called rational numbers, right? And the notation for rational numbers are Q, right? Then irrational numbers. Irrational numbers are not denoted as this R/Q. This means from real numbers, take out the rational part. Then what is left is the irrational numbers. It's also denoted by Q dash. So Q dash or R/Q is the notation for irrational numbers. So irrational numbers are what? Non-terminating, non-recurring decimals. You can think of irrational numbers as non-terminating, non-recurring decimals. So examples are square root 2. So there's no pattern for this decimal. No, 414 next number. There's no pattern here. That is, there's no recurring decimals. And it doesn't stop. So these types of decimals are called irrational numbers. Another famous irrational number is pi, 3.14, so on. That's also non-repeating, non-terminating number. Some more irrational numbers are root 3, root 5, root 6, so on. Those are all irrational numbers, right? So now we have discussed real numbers, integers, natural numbers, rational numbers, and irrational numbers. So now let's look at the order of these things. Which set is the biggest, which set is the smallest out of these, right? So if we look at this, natural numbers, integers, rational numbers, and irrational numbers are all subsets of real numbers. So which one is the biggest real numbers? So R is the biggest set, like shown here. Then inside R you have what? Rationals. So Q is a subset of R. This C like term is subset. This is a symbol for subset. Subset. So Q has to be inside of R. Then inside of rational numbers, what do you have? Integers. So integers are a subset of rational numbers. Then inside of integers, you have what? Natural numbers. So positive integers are inside of integers. So natural numbers is the smallest set out of the 4 number types we discussed. Then there's this one. Q dash is what? Irrational. No. Irrational is what? R/Q or what? From the real numbers, you take out what? Q. So I have to remove Q from the real numbers. So that in between part, this part, between real and Q, That part is what? That part is Q dash or irrational numbers, right? So that is the order of these sets. R is the largest set, N is the smallest out of these sets, right? Okay, then next topic, surds. What is a surd, right? So let's read the definition. If x is a positive integer with nth root, then this one, nth root of x is a surd of nth order when the value of nth root of x is irrational. When this value becomes irrational, then what? Then this is called what? A surd of nth order, right? In this expression, n is the order of the surd, x is called the radicand. Whatever we put inside the root is called radicand, right? This is something you can remember to easily identify a surd. When it is a root and irrational, it is always going to be a surd, right? So let's look at the examples. Root 3. This is what? A root and a irrational value in a root 3. There's no way to write this as a repeating or terminating decimal. So root 3 is an irrational number. Then this one, fifth root of 13, that is also irrational. Then how about this one? So this is order 5. Surd, this is what? Order 2, square root. No? Then let's look at this one. Why is this one a surd? This is what? 4 raised to 1/4 power. Oh, this is same as 4th root of 4. So let's simplify this. 4 can be written as what? 2 squared 1/4. So simplify this, what do you get? So you can multiply the indices. No? 2 into 1/4 is half. 2 raised to half is what? Square root 2, which is what? Which is irrational. So then the value of this is an irrational number. 4th root of 4 is irrational. Then that means what? 4th root of 4 is a surd of 4th order. Right. So that is how you identify surds, right? So for square roots, there's an easy way to identify surds. This works for square roots, okay? Any number. So now look at, I have written 4 numbers, 4 square root numbers. If the number inside is not a square number, these numbers are going to be surds because they are going to be irrational. But if the number inside is a square number, like this, 9 is a square number. 9 can be written as what? 3 squared. So this is a square number. So then this becomes 3, no? So then any number that is a square inside, it won't be irrational. It's not going to be a surd because you get a rational number back. But inside a square root, if you have a non-square numbers, like 6 is non-square, 7 is non-square, 8 is non-square. So all 3 of them are irrational and surds. Right, remember that trick. This works for square roots. If the number inside of the square root is non-square, it's automatically a surd, then it's a irrational, right? Okay, now let's do some questions involving surd simplification, right? So we want to simplify each answer, work out these surd, right? So let's look at the first one. What's the first one? We want to simplify 4 root 50, right? So this is how you do this. The inside number, look at the inside number. Write the inside number as a square number times another number, right? So here I can write this as what? 50 can be written as 25 times 2. 25 is a square number, no, why? 5 square is 25. So 25 is the square number. So 5 square times 2. So you have to write the inside number as a square number times another number, right? Then 4 root 50 is same as 5 square times 2 inside, right? Then we can break it like this. Square root of 5 square times square root of 2, right? Here I used a property of square roots. If you have a product inside a square root, I can break it into this way. I can break it into square root of a times square root of b. You can do the same thing for division. If you have a division or quotient inside a square root, you can write it as square root a over square root b, right? So I used that property and broke this into 2 square roots, right? Then what is square root of 5 squared? Square root of a square is what? You just cancel the square root and the square. So you get what? You get 4 times 5 times square root 2. Square root 2 we can't simplify, no? It's a surd. So it's already simplified. So 20 square root 2, right? So that is how you simplify these types of questions, right? So now let's look at the second one. Square root 22 into square root 10, right? So now I'm going to use this property again. I can write it under 1 square root. In the first one I went this way, no? From 1 square root to 2 square roots. Now from 2 square roots to 1 square root. So then I can write this as what? 22 times 10 inside, right? Then I need to find a square number inside to get out. So I can write what? 22 in factored form is what? 2 times 11. 10 can be written as what? 2 times 5. So now I can create a square number, no? 2 times 2 is what? A square number, no? 2 squared times 11 into 5. Right. So 11 into 5, we can't simplify further, no? So you can write it as 55. So now again use the square root property. Now break this into 2 square roots. Square root of 2 squared times square root of 55. Then square root of 2 squared is just 2. Then 55, square root of 55, we can't simplify further because why? This is not a square number, no? There's no square number inside also. This is the most simplified form of this. So this is the answer. 2 square root 55. Right. Now let's look at the third question. Right. So now we have what? 12 square root 10 over 3 square root 5. Right. Now I can first simplify the outside part. That is 12 over 3, 4. 4. Then what I'm going to do is this square root 10 and square root 5 I'm going to write under 1 square root. Like this property of square roots. Square root a over square root b is same as square root a over b inside. So using that I can simplify this. I can write it as what? Square root of 10 over 5. So that is square root of 2. So the final answer is what? 4 square root 2. Right. Then let's look at the fourth one. Square root of 50 plus square root of 8. Right. So this is similar to the first question. Instead of one term, you have two terms, but the simplification is the same method. Write the inside number as a square number times another number. This also write as a square number times another number. So what is 50? 50 is 25 times 2 or 5 squared times 2. What is 8? 4 times 2, that is what? 2 squared times 2. So we can use that, right? So this you can write as what? 5 squared times 2. This you can write as 2 squared times 2. Then this breaks, no? 5 squared becomes 5 and you have square root 2. 2 squared you can take the 2 out and only square root 2 is left. Then we can add these, no? They have the same form, no? Square root 2 terms. So this is like take the common part out, square root 2 out, then you have what? 5 plus 2, no? So this is actually 7 square root 2. Right. So then fifth one is a similar question, right? Let's do the fifth one. So what do we have? 4 root 27. 4 root 27 minus square root 75. Right. So now write 27 as a what? Square number times another number. So 27 is what? 9 times 3. That is what? 3 squared times 3. That's the square number times another number. 75. What? 25 times 3. So 5 squared times 3. So we can use those two. Right. So then this can be written as what? 4 square root 27 can be written as 3 squared times 3 minus this one can be written as 5 squared times 3. Then this part 3 squared becomes 3 outside. So 4 times 3 times square root 3. This one 5 comes out. 5 times square root 3. So simplify, you get what? 12 square root 3 minus 5 square root 3. So that is what? 7 square root 3. Right. So then the last one. Let's see what's the last one. Right. Multiplication. Right. 3 plus square root 5 bracket 4 minus square root 5. So get rid of brackets. 3 times 4. So this one. First 3 times 4 is 12. Then 3 times square root 5. So it's minus square root 5. So minus 3 square root 5. Then we are going to do these two. Square root 5 times 4. So that is going to be 4 square root 5. And the last two, square root 5 times minus square root 5. Square root 5 times minus square root 5. So it will become minus square root 5 times square root 5. So now simplify. 12 plus square root 5. What happens here? Square root and square root cancel and you get what? Minus 5. So answer is what? 7 plus square root 5. Right. Here we can cancel the square root because number is the same. So this is same as what? You can write this as what? Square root 5 times square root 5 is what? Inside 5 times 5. So that is what? Square root of 5 squared. That is just 5. Right. So this is the answer for that one. Right. Okay. Next type of question you will encounter is when you have quotients where the denominator is a surd. We want to get rid of that. We want to rationalize the denominator. Rationalize the denominator means you can't have irrational numbers or surds in the denominator. So we have to get rid of the irrational or the surd part out. So that is called rationalizing denominators. Right. So let's see how to do that. Right. The first type is the easiest type. So you have a number like this where the denominator is made up of just a surd. Then the method is multiply both the numerator and the denominator by the denominator surd. Then what happens? You have what? 7 square root 6 in the numerator. In the denominator, what do you have? Square root 6 times square root 6. Square roots cancel out and you get a 6. So 7 square root 6 is same as 7 square root 6 over 6. Now the denominator is rational. It's not a surd. So this is called rationalizing the denominator. Right. Then let's look at the second one. Second one is similar. So what you need to do? So we want a equivalent expression. So again, denominator is made up of one term. No? So then you multiply both the denominator and the numerator by that term. That's all. So then simplify. 2 minus square root 3 times square root 3 in the numerator. Square root 3 times square root 3 becomes 3. Then distribute the square root 3 in the numerator. So you get what? 2 square root 3. Square root 3 times square root 3. Again square roots cancel. You get minus 3. Whole thing over 3. So again look. Denominator is rationalized. There's no surds. So this method is called what? Rationalizing the denominator. So these are the first type of questions you will encounter where you only have what? One surd term in the denominator, right? Then the next two, look, you have two terms. So then there's a different method for doing this. So let's look at those two types. Right. So look at number 3. Right. We have two terms, not a single term. Then we can't just multiply by square root 3, the third part. So when we have this type, this is what you do. Then you have this type. To get the equivalent value, equivalent expression, you multiply both the denominator and the numerator by this. So again look at the denominator term. Now you have 6 minus root 3. No? Just change the middle sign. That's all you do. And multiply by that number both the numerator and the denominator. So what do we do? If you have a minus here, you change it to plus. If you have a plus here, you change it to minus, right? This method is called multiplying by the conjugate of the denominator. So how do you get the conjugate? If you have a minus, change it to plus. If the middle sign is plus, change it to minus. That's all. After that, just simplify. So here, to simplify the denominator, you can use a trick, easy trick. Remember this a squared minus b squared formula. That is what? Difference of squares. A minus b plus times a plus b. So here look, what do we have in the denominator? 6 minus root 3 times 6 plus root 3. So this follows the difference of squares formula. This follows difference of squares formula. A is like 6, b is like square root 3. So a minus b times a plus b. So that should be equal to what? A squared, which is 6 squared, minus root 3 squared. So 36 minus 3, or 33. So you can use that trick to simplify the denominator when you are doing rationalization, right? Okay, now let's simplify everything and get the answer. So I have 3 root 6 times 6 plus root 3 in the numerator, and the denominator becomes what? 6 squared minus root 3 squared. Now expand the brackets in the numerator and simplify. So you get 18 root 6 plus what? 3 root 6 times root 3 divided by 33. Then let's simplify this. 18 root 6. These two put under 1 square root. So 3 square root 18 over 33. So now we can simplify it further now. 18 square root 6. 3 square root 18. Square root 18 you can simplify now. That can be written as what? 9 times 2 divided by 33. 18 square root 6. This is what? 9 is what? 9 is 3 square. So you can take a 3 out now. So you have what? 3 times 3 square root 2 divided by 33. Right. So now notice this number has a multiple of 3. This number has a multiple of 3. 33 has a multiple of 3. So you can cancel a multiple of 3 or 3. So this will give you 11. 1 3 you can cancel. 18 divided by 3 is 6. So now you can write the final answer. So you have what? 6 square root 6 plus 3 square root 2 divided by 11. So the denominator is rationalized, right? Okay, let's do the last one. So 1 minus square root 5 divided by 1 plus square root 5. So again, there's two terms, no? So then you use the conjugate method. So we multiply both the denominator and the numerator by conjugate of the denominator. Denominator is what? 1 plus square root 5. Then what is the conjugate? 1, change the sign. What is the sign? This is plus, so the conjugate will have minus. That's all. Right, now simplify. So I have 1 minus square root 5 times 1 minus square root 5 in the numerator. Denominator, simplify using the a squared minus b squared method. Then get rid of the brackets, expand and simplify the numerator. So you will get what? 1 minus square root 5 minus square root 5 minus square root 5 minus square root 5 is plus 5, right? Because minus minus becomes plus and the square roots cancel, right? Now simplify. We have 1 minus 5, then you have what? 6 minus 2 square root 5 divided by minus 4, right? Again simplify as much as possible. So all of them has multiples of 2, no? So this 2 cancel, you have a 2 here, you have a 3 here. So 3 minus 2, sorry, no 2, you cancel 2, 3 minus square root 5 over minus 2, or you can write it as what? Square root 5 minus 3 over 2. Both are correct, right? So that is how you rationalize the denominator. If it is just a single surd, you just multiply by that, both the numerator and the denominator. If there's more than one term with a surd in the denominator, you multiply it by what? Multiply the numerator and the denominator by the conjugate of that. Conjugate is what? You just change the middle sign. Minus becomes plus. In this question, it was plus, no? So plus becomes minus, right? Okay. So that is what we are going to cover in the first lesson of algebra. How to rationalize denominators and how to simplify surd expressions, right? Okay. So I will see you guys in the next lesson.